Hey guys, I think we're going to get started here. So this talk is called New Data Architectures for Network Flow Analytics. And before just jumping into the talk, I want to give you guys a brief introduction of myself. My name is Fanjin. A lot of people call me FJ. And I'm a co-founder of a technology company based out in the Bay Area called Imply. And actually, prior to the startup world, I spent most of my career in building highly available, highly scalable distributed systems. So this talk will actually focus a lot on my experience on working with network flow data and building out different types of databases and data systems for network flow data. So just a brief overview of this talk. What I'm going to be covering is really some of the problems I see today with network flow analytics. I'm going to be talking about different technologies that can be used to solve some of these problems. I'm going to be talking about a class of databases, a new class of databases called operational analytic databases. And I'm also going to be talking about an open source project called Apache Druid, which is something that I work on that's going to relate to this whole idea of operational analytic databases. Then I'm going to be going into details about the architecture of how these operational analytic databases work and how can they be deployed in practice. And at the end, we'll take a few questions as well. So just getting started, I'm going to start with some very high-level problems, then get into increasingly more detail, more sophistication around some of the problems I've seen with network flows. So very high level, I think we all know this, network flow data continues to grow in scale and complexity today, especially at major enterprises. More applications are being deployed on the network, and it's very, very critical for analysts, operators, and even monitoring teams out there to understand the performance of their network and also to be, as quickly as possible, able to troubleshoot issues in the network. So this data, it can be flowing in real time. A lot of operators are working with live data about their network, but historical data is also important as well in order to understand anomalies, in order to understand problems in the network, especially what's happening right now. You have to understand what has happened in the past. So talking very broadly about the data, flows, they can come in many different forms. You can have netflows, flows, IPFix, et cetera. Network data can oftentimes also be enriched with application level data, so information about the types of applications running in the network, as well as user data, so what types of users are using what types of applications. What's pretty common with network flow data that I've seen is there's really three types of components to this data. So one, there's a timestamp, and this timestamp indicates when the flow is created, when it occurred, when some event occurred. And then there's a set of attributes or dimensions. So these are properties that describe the flow. These are things like your source address, source port, destination address, destination port, and so on and so forth. So attributes or dimensions are things that you would group on as you do your analysis. And most of the time, as part of your analysis and part of your data, you also have a set of measures or metrics as well. So these are the numbers you actually want to crunch as part of any sort of analysis with network flows. So these are things like just a number of flows, it could be a number of packets, it could be bytes per second, it could be quantiles and histograms on performance of the network, and so on and so forth. So measures are usually numeric things that you want to crunch, and dimensions are things that you want to group on. So the use case with network flow data, as I mentioned, very high level, we want to be able to monitor the network. We want to be able to proactively detect issues. And when issues occur, we want to resolve them as fast as possible. Going into more detail about what does it take to resolve issues with flows, what does it take to resolve issues in your network, usually the types of queries that are made on top of this flow data tends to be rank in order. So for example, for a given destination address, I want to see the top sources addresses that it came from. Or it could be a lot of different types of top ends on various attributes of the network. A lot of queries also involve search and filter, so perhaps you want to be able to resolve issues on a particular subnet address or on a particular single IP address. So for the system used to power these types of queries and to be able to answer these types of analytic queries, we want our analytic system in general to be very cheap, very efficient, because there's a lot of network data and we don't want to spend that much money on hardware. Okay, so before kind of just jumping into data architectures and jumping into and classifying different types of systems, I thought I would just go through a video of a very quick demo just to showcase what it means to diagnose something interesting within network flow data. And this is really just to provide context for the rest of this talk as we start going through different types of architectures. So this video and this demo is really just about UI that's being used, that's being powered by some of these data systems I'm going to be talking about a little bit later, and how this UI can be used for solving different types of problems with flow data. So I don't know if there's actually any sound with this video, so I'm basically just going to kind of commentate over what's happening here. So this is a UI describing flow data. This is actually live data that's coming from Imply's own network, and our infrastructure is actually being entirely deployed in AWS today. So on the left-hand side, you see those dimensions and attributes of flows I'm talking about, like the interface, the action, source, destination address. On the right-hand side, we have various types of measures. In this example right now, we're really just looking at like a count of flows. And at some point, I'm going to actually, I think when I recorded this video, I'm going to start dragging and dropping different attributes into the center and going through a workflow of basically diagnosing and understanding why traffic is getting rejected in our network. But right now, I think so if you see on the right-hand side, it's just a bunch of different types of measures or metrics related to flows, things like bytes, bytes per second, bits per second, percentage of traffic that's accepted or rejected. And with any good kind of network flow system, we want to be able to slice and dice these metrics based on the dimensions and attributes of the data. So here, what we're looking at is we're just looking at a count of flows over the latest hour. There's various other views we can look at. We can look at maybe the latest 6 hours, latest day. By dragging action to the center, what we're looking at are the actions that are happening actually in our own internal network, which percentage of traffic is accepted, which percent is rejected over the last hour. And I believe what I'm going to do now is actually just filter in and really look at the rejected traffic. Because as you can see here, there's a non-trivial set of flows in our network that's being rejected. So the immediate question that comes is why? Why are so many flows being rejected? What's the cause of it? So one of the things we might investigate right away is the destination port in which the rejected traffic is happening. And what we can actually see here through this UI is most of the rejected traffic is actually happening on port 6379. And maybe we actually want to understand on port 6379, what are the top destination addresses in which flow traffic is getting rejected on. So here we see a particular IP in our network is where the vast majority of rejected flows is coming from. So we can actually search, filter, and focus entirely on this IP and look at the service name of this IP, in which in this case it's an unmanaged service name. Next thing we may want to do, knowing that a given IP is where most of the rejected traffic is coming from, is look at the sources of that traffic. So in this case, what we see is actually two IPs generating extremely uniform traffic. So these two sources, just comparing their traffic, it looks like both of these source IPs are generating extremely uniform traffic against one of our destination addresses, and we're rejecting all of that traffic. So the workflow that I'm trying to showcase to you right now, and the workflow that I want to be talking about a little bit later on, is this one of being able to arbitrarily slice and dice flow data and really start examining it based on an arbitrary set of attributes to try and understand why rejected traffic might be happening. So in this case, what we see is there's two IPs that's issuing live traffic to one of our destination addresses. We're rejecting all of it. We're looking at this traffic on a minutely basis, and it seems like actually every 3 seconds, one of these IPs is issuing a request. So this clearly seems like automation against one of our internal servers. And actually looking into what these source IPs are, these are actually like Amazon servers, which is kind of interesting. So it's probably some other organization that's deployed in AWS trying to connect to us. But hopefully that gives you an idea of kind of the analytics workflow, the exploratory workflow, the investigative workflow that we want to start doing with flow traffic. So Some of the challenges of being able to investigate flow traffic and understand why certain things are happening, why trends, patterns, or anomalies are happening. Some of the challenges are just around the scale and infrastructure required to handle the data, and some of the challenges around enabling very fast investigative queries on the data. So looking at flow data today, if you're a pretty large enterprise, if you're dealing with a non-trivial set of flow data, you're probably dealing with millions of events per second. And most of this data is coming in real time. However, you might have a bunch of historical data about your flows as well. This data, as I mentioned at the very beginning, is becoming increasingly complex. So complexity really relates, in my world, in my mind, to dimensionality and cardinality. So dimensionality is about having many different attributes in your flow data. So everything about the interfaces, everything about the source destination ports, and potentially enriching this data with application information as well. Cardinality is this term to describe the number of unique values kind of within a single dimension. So if one of your dimensions is IP address and you have millions of IP addresses and you want to rank them on some particular metric, that can be a very complex, very difficult operation to do if you have a lot of unique IP addresses or a lot of unique values within a single dimension. Another one of the challenges of working with flow data is just around the structure of the data. So more and more so, flow data is becoming unstructured. It could be arbitrarily nested. You could have JSON blobs which don't have a predefined schema to them. The events from time to time are evolving and constantly changing. So your schema from 1 hour to the next hour might be very different because you're seeing very different types of events. So these are all challenges around both storing and computing kind of the base flow data that we're working with. Now, in terms of accessing the data, more and more so, people are not issuing SQL queries, they're not issuing programmatic queries against the data. People are leveraging UIs to investigate and understand flow traffic. So a good UI needs both reporting and exploring capabilities. And to leverage the UI in order to do troubleshooting, you have to have very fast search and filter. You have to very fast drill down. And this allows you to very quickly slice and dice the data to pinpoint various issues within your flow traffic. And then the last kind of challenge with UIs in general is in most enterprises I see today, there's really kind of one central team that's providing flow analytics out to many different other teams that require this data. So there's this idea of multi-tenancy in UIs, which is being able to support potentially thousands of concurrent users trying to access the same data at the same time. Right, so to solve these challenges, to really build a system that's great for understanding flows and for troubleshooting and investigating issues that we see in flows, there's a lot of different technologies that we consider. And there's kind of three broad classes of technologies that I see the most oftenly deployed. So these technologies are log search systems. So this is the ELK stack. These are search systems such as Splunk and other systems in that category. Another data system I see often are analytic query engines. So sometimes these are traditional analytic databases such as Vertica. Sometimes there are new SQL Hadoop solutions such as Presto. And then the last set of technologies I see commonly deployed are time series databases. So systems such as OpenTSDB, Prometheus, and InfluxDB as well. And I'm just going to actually talk about some of the advantages and disadvantages of these different types of systems, and then discuss this idea of operational analytic databases, which is a new architecture that's potentially, in my mind, solving some of the issues that we see with these three legacy classic approaches to handling flows. So the first set of systems are log search systems. So this is very commonly, I see this used with network traffic, so the ELK stack and also Splunk as well. Some of the major advantages of systems like Splunk and Elasticsearch. One is they're very good at doing real-time ingest, so you can feed in live flow traffic. They're very good for being able to handle semi-structured and unstructured data, so you can have arbitrarily nested blobs of JSON and Avro and other data formats you can just kind of feed into these systems. And then they're also very good at fast search and filter. So investigation in flow data oftentimes requires very fast search and filter. The problem that I usually see talking with different people that use these systems is around performance. So one, systems like the ELK stack and Splunk, they're not they're not the most performant when you have high dimensional, high cardinality data. So if your flow traffic doesn't have 5 attributes, if it has 50 attributes, if it has 100 attributes, and you want to group on, rank, sort, and order all of these different attributes, you want to slice and dice across all these attributes, then a lot of these log search systems start really slowing down in terms of performance. Another drawback I've heard often around log search systems is their performance for numerical aggregation. So if you're just crunching the number of flows, maybe you want to count the number of unique devices that are available in your network, or these types of queries that require adding a bunch of numbers together. This is fundamentally not what the ELK stack, fundamentally not what systems like Splunk are designed to do. They're really designed for search and filter, and not so much for metric aggregation and crunching numbers. So what is designed for very fast analytic queries that involve crunching numbers are what are known as analytic query engines, or OLAP systems. So systems like Vertica, systems like Presto, even more old school data warehouses like Teradata. And the way that a lot of these databases work is they have a column-oriented storage, which makes them really, really good for crunching numbers. They're designed to support large, complex group bys. They're designed to support all different types of complex aggregations. So you can build histograms, you can build quantiles, you can calculate rates of a lot of different types of flow traffic. The main drawback of a lot of analytic databases actually are probably on the ingest side. So they're not really designed for real-time ingest, so they're not really good for streaming and flow traffic. They really require DBA to start designing schemas. So if your flow traffic has nested JSON or has an evolving schema, these types of systems are not really built to deal with changing schemas. And the final thing is, most analytic query engines, things like Presto and Vertica, are very slow for search and filter. This means that if you want to start doing investigation by ad hoc analysis of your data, this is not a super great fit. Last set of databases here that I see starting to get more popularity are systems such as Prometheus, InfluxDB, or OpenTSDB, which are time series databases. And the way that time series databases work is that they're very, very efficient for adding numbers and then partitioning and filtering on time. So time series databases have time-optimized sharding, they have time-optimized storage, and then you can aggregate metric values extremely quickly. The main drawback that I've heard with systems like Prometheus and InfluxDB is that they're very slow when you start grouping, ranking, and sorting on your dimensions, which are not time. So if you want to look at a given source IP and then all the destination IPs that feed into that source IP, and maybe all the interfaces across all of those destination IPs, this is a 3-level multidimensional group by. This is something that time series databases are not really designed to do because it's a pretty complex analytic queries. And then the other drawback of time series databases is they're not great for search and filter. So as you start doing more investigations, they're not great for fast slice and dice. But what I want to try and highlight, why I talked about 3 different classes of data systems, is each of them has attributes which make them really ideal with working with network traffic data, with network flow data. And really recently, we've seen a new class of data system that's starting to emerge. Then the whole idea behind this class of data system is trying to combine ideas from time series databases, from analytic databases, and also from log search systems as well. And this new class of data system is designed to try and remove all the cons of these 3 types of databases and merge all the pros together. So I don't think there's an industry standard term for this class of database yet. However, I'm going to kind of make one up and call it an operational analytics database. And the whole idea behind this new class of systems is trying to combine the benefits of time series, analytic, and log search systems. So this new class of database, what it can do is it can provide the ingest and the search and filter capabilities of systems like ELK and also Splunk. They store data fundamentally in a column format, similar to Vertica, similar to Presto. So the idea is you can have all the query and analytic capabilities of some of these analytic query engines. And then these data systems also have time-specific sharding, time-specific optimizations, similar to systems like Prometheus and also Influx as well. So the overall idea is we can do the best of all 3 worlds. So there's a bunch of different types of operational analytic databases. At one point in time, there's really only one, but now I would say there's 5 or so that I hear about pretty frequently. I'm one of the committers on Apache Druid, so I'm obviously very biased in that I think it's the most popular operational analytics database out there, and a lot of this talk is going to focus on the architecture of Druid. However, there's Scuba at Facebook, so for folks that work at Facebook or may have interacted with Facebook, Scuba is an example of an operational analytics database that's used for all different types of workloads at Facebook. There's Pinot that's coming from LinkedIn. There is Paolo, which actually I think is now called Daisy, that's coming from Baidu. And then there's ClickHouse, which is made by the Russian search engine Yandex. Basically, these 4 or 5 systems architecturally are virtually identical. They all have the same ideas. They all combine ideas from these legacy systems. Their storage formats are almost identical as well. So how they store data, how they query data, their fundamental architecture is very, very similar. So I'm going to talk about how these operational analytics databases work, but I'm going to be using Druid as a case study because 1, it's an open source project. It's incubating in the Apache Software Foundation, and 2, it's because it's the one that I have the most experience working on, and I understand the architecture the most deeply. So Druid runs in production at many different companies of many different sizes. I just put up a couple of links that you can find on the internet about how various people are using Druid. It is very, very commonly used for network traffic, network flow analysis, and investigation as well. So how does Druid store data? So let's look at some raw data right now. This might be just some raw flow data, so there's a timestamp of when the flow occurred, and then just for simplicity's sake, there's only 2 dimensions. There's an action, which was the traffic accepted or rejected, and what was the sort of the protocol of the flow, and then just a count of flows for a particular period in time. So the first thing that Druid actually does with the data is a pre-aggregation or summarization step. And in the summarization step, what Druid is going to do, and this is something that's optional, is it's going to truncate the time in which raw data appeared at, and it's going to try and find commonalities basically in the dimensions of the raw data. So in this case, we're truncating data to an hourly granularity, and you can see that once we truncate the timestamp, basically there's a bunch of different rows that have the exact same set of attributes, and what we can do with this flow metric is we can just aggregate it together. And this in practice can be very good at reducing sort of the raw data you actually end up storing in the system. What you trade off is information about the time in which events occurred, but what you gain is potentially a lot of storage savings and also performance improvements as well. And in this example, we're not losing any fidelity of the data, so this flows metric is still going to be accurate for the given timestamp. The next thing that Druid and all these operational analytic databases do is they partition data by time. So this is how every time series database works, and this is how Druid works as well, where once we roll up the data, then we look at, can we split this data up by time in some meaningful way? So in this example, what we're actually doing is we're partitioning data based on hours. So every shard of data, every partition of data within Druid is representing an hour's worth of flows. In practice, each one of these shards or segments is containing millions of rows of actual data. But this level of partitioning allows us to do very quick queries based on time. So if we're only querying for an hour's worth of data, we don't need to hit all these other shards. We can actually just find the shard that contains the hour's worth of data that we care about and only scan that data. So it's one of the performance improvements of our operational analytics database. So these shards or segments in Druid, they are a very fundamental storage unit. They're basically immutable once they're created, and they're designed to be very read optimized. So we don't have this contention between reads and writes. Basically, once a segment is created, it's designed to be read as fast as possible. And the parallelization model, how an operational analytic database actually scales is you have kind of one thread allocated to one segment at a time. So when you add more CPUs to your cluster, you can scan a lot more data in parallel. So I talked a little bit about how Druid looks like a time series database and how it partitions data based on time. This is really about how Druid looks actually like an analytic database in that it stores all attributes and all dimensions fundamentally in columns. So column stores in the analytic database world are known for being able to aggregate numbers very, very quickly. They're also known for being very good at compressing different types of attributes. So in this case, this is an example of something called dictionary coding. The idea is in our flow data, we might have an action dimension and a protocol dimension, and we might have two values for action, accept or reject. And as opposed to storing these variable length strings directly, we can actually assign an integer value to each string. So accept gets assigned to a value of 0, reject gets assigned to a value of 1. And in terms of the protocol, TCP might get assigned to a value of 0, UDP gets assigned to a value of 1. So when we actually end up storing this data within our database, we're not storing these raw strings. What we're storing is integer encoded IDs. And then there's a lookup between the integer value and then the string value. And in practice, especially when you have a high cardinality dimension with a lot of string values, this can result in significant storage savings. One other thing here, so Druid also looks, in all operational analytic databases, they also look in part like a search system, so they look a little bit like ELK as well. And the idea is that we can create different types of search indexes for very fast search and filter. So in this example, basically we have our action attribute, which has two values, accept and reject. We can actually create a lookup which tells us in which rows the accept value is seen and which rows the reject value is seen. So accept is seen in rows 0 and 1, so we can build this binary array that basically, so we have a laser pointer here, that basically indicates that accept occurs in these two rows and doesn't occur anywhere else. Reject only occurs in these 4 rows and not anywhere else. And the idea is when we issue a query just on all of our rejected traffic, we don't have to scan through all of our data. We can actually just look at rows 2, 3, and 4 and add up the number of flows in those rows. And this is something that all search systems do for very fast search and filter, for very fast investigative analysis. And similarly, because with these binary arrays indicating where values exist or don't exist, we can do Boolean operations over them to basically indicate which rows contain either the accept value or the reject value. So in this case, it's actually every row. And of course, a lot of these indexes can be compressed as well. Kind of one last thing I want to talk about related to storage is approximation algorithms. Many aggregations in the network flows world don't quite require exactness. So for example, count distinct, histograms, and quantiles, and different forms of set analysis. You don't have to do these exact anymore. Most of the time what people are looking at are general patterns or trends to see if the changes or the deltas are actually meaningful. And because we don't need exactness always, then we can start leveraging approximation. And approximate algorithms can be very powerful for providing fast queries while kind of reducing the storage requirements. And just kind of give you an example here. So this is how Druid does rollup. I talked about this a few slides ago. If we were to enrich this basic flow data with a device ID, so maybe we want to understand all the devices running on our network, and we have a lot of unique devices, this basically prevents our ability to roll up the data and really get those storage and performance benefits. So as opposed to storing every single unique device ID, we can actually store an approximation of the number of unique devices that we've seen. And this is something very powerful where we actually convert device ID into an approximate metric that allows us to roll up our data again. And this allows us to get all the storage and performance benefits of having a smaller, reduced data set. Okay, just going into the architecture of these operational analytic databases, pretty much Scuba, Pinot, ClickHouse, Druid, all of these architectures are pretty similar. The architecture of Druid is that of you can think of it as kind of a disassembled database. So there's different types of processes, and each process can be kind of fine-tuned depending on your workload. And the idea is you would have some raw data either in a file system. The raw data could be a stream of data, it could be collected, it could be something in Kafka. And what Druid is going to do is it's going to convert raw data into this optimized partition segment format. So the segment I talked about a few slides ago is this column-oriented storage with search indexes built in that's time partitioned. And that's the thing that Druid is fundamentally working with for all queries. So you have raw data that's getting converted into segments on an indexing process, and then these segments are loaded across a set of historicals, and historicals are processes that are basically designed to read segments, and that's pretty much all they do. And then you have a set of processes called brokers, and brokers are responsible for kind of query, scatter, gather. So the idea is queries will hit a broker. Brokers know which segments are getting created live on the indexers and which ones are already completed and living on historicals. So brokers do query, scatter, gather. These guys kind of crunch their portion of the answer in parallel and then return results to the query broker. And then the broker unifies all results together. And then how do you actually query these things? There's JSON over HTTP, SQL, R, Python, Ruby, pretty much whatever language you're comfortable with, you can actually query Druid with. So by the numbers, most of these operational analytic databases are designed to scale to, they're all designed to be horizontally scalable. They're all designed to deal with some pretty tremendous volume. Druid in particular has a lot of public information about some of the size of the clusters out there. So some of these clusters are now at 100 trillion raw events, ingesting more than 300 billion events daily. And even on clusters of this size, there's average query latencies of about half a second. So really, when your query latencies become less than a second, you can start doing really fast slice and dice queries through a UI. You can start really exploring, doing ad hoc analysis of data. And this is, I think, very important in the netflow world. And some of these benchmarks were presented on a data set that has about 30 dimensions or 20 metrics, which is similar to what you would see with netflow data. So the last thing here is just kind of end-to-end architecture. Where would you deploy an operational analytics database? How does it fit into a modern data stack? So the modern data stack that I see most common within the enterprise today is one where there's really dedicated systems for dedicated workloads. So the most common thing is you would have raw events that get created somewhere, and then they're either collected through some sort of collector, and then they're fed into a message delivery system known as a message bus. The most popular message bus I see is probably Apache Kafka. I see a lot of netflow data go through Kafka today. There's other message buses in Amazon. There's AWS Kinesis. There's Google PubSub, and I think Microsoft has their own thing as well. So the next stage after data is kind of collected and being delivered to the message bus is through some sort of data processing or ETL system. In the netflow world, the most common path is through some sort of stream processor. So the idea behind the stream processor is to enrich the netflow data, to add things like application information, potentially adding user information as well. So the stream processor, popular systems out there include Apache Flink, Apache Samza, Kafka Streams. They're all designed to do the same thing. They're designed to transform and enrich underlying raw data. And then finally, where the enriched data ends up is in some sort of query layer. So in this case, it's going to be Druid. So the end-to-end architecture looks like I collect flows from somewhere, I put it into Kafka, maybe from Kafka I'm going to deliver it to a file system, maybe I'm going to deliver it to my ETL layer, and then I'm going to put it into a serving layer where my queries or where my users are going to interact with it, where my applications are going to start talking to it as well. So Druid being an open source project, it really works out of the box with a lot of other open source projects as well, and we're really big believers in sort of a more disassembled data stack nowadays. So Druid works out of the box with message buses like Kafka, Kinesis, Google PubSub. It works with file systems like Hadoop, S3. It also works with stream processors like Spark Streaming, Flink, Storm, and others. So just to kind of summarize this talk, I think operational analytic databases, I think they're very useful in the netflow world. I think They're very helpful for being able not just to do analytic queries and not just to do search and filter queries, but to really be able to do different types of search and investigation, as well as reporting and monitoring. And as I mentioned, Druid is a project that's incubating the Apache Software Foundation. It's a community-run project. There's about 10 or so different companies that are actively contributing to it. We have a community webpage that you can go to and you can download it. And then there's also sort of an enterprise-y version that we host on Imply as well. So with that, that's my talk, and I'm happy to answer a couple of questions if anyone has any at this time.
Hi, Igor Gashinsky, Yahoo/Oath. We use a lot of Druid in a bunch of our operational analysis engines. One thing that I kind of uncertain about is the use of Druid for flow. The way that I see it is that flow has a couple of use cases. Flow could be real instantaneous. I need super high fidelity of data, what happened in the last 5 minutes, and I need super high fidelity. Doing any sort of roll-ups that you're suggesting will completely make that go away. Then there's what you're suggesting, which is roll up to 5 minutes. I probably want to keep that for about a month. But a month ago, every 5 minutes roll-ups are kind of irrelevant. So like, how do you see this architecture where you almost have 3 different tiers of data that needs to be available, all as a fast set search, which is ultra high fidelity, high resolution, last hour or so to help operational troubleshooting, break fix, like very high level of data, and then what happened over the last 5 years showed me a trend which also has to be aggregated probably by interface, by property, by customer type, tons of different dimensions. And if you're doing aggregation that does approximation, which I'm not quite sure what you meant by that, but if by approximation you mean loss of accurate data of this was customer A versus customer B, that might be an issue. Like, how do you deal with that?
Yeah, so the very short answer is actually in Druid today, all the rollup, all the approximation is optional. So you can actually disable rollup and just maintain your raw data. So one very common model that I see is people don't roll up raw data for a very recent span of time, whether that's the recent hour or the most recent day. They basically just keep the raw data around. And then because historical data is also important and it gets prohibitively expensive to store flow data for up to like 2 years, then there's different levels of rollups that start getting applied across a timeline. So for example, you might keep the most recent day of the raw data and the most recent month rolled up to 5 minutes, and then everything older than that rolled up to like an hourly granularity. Because as data gets aged out, I've just seen most people don't need to query like what happened at precise millisecond in time. It's actually more about broader trends within the data. So that is something that Druid does support today, and it's very common now for people not to roll up data. The second part of that answer is we believe in a lot of like disassembled architecture, so pulling raw data from like a message bus such as Kafka. So for both Kafka and Kinesis, we actually are providing very strict guarantees on data loss. So we actually guarantee no loss of data, no duplication of data. So we're guaranteeing exactly once consumption semantics. And that's with the overall idea that your whatever queries you issue are going to be 100% accurate. So all the approximation can be turned off. There's obviously going to be performance and storage trade-offs there, but if fidelity of your data is important, then that is something that's being strongly supported today.
So what would the performance implications be if you turn off all those rollups?
It really depends on what your data looks like. So with some data sets, people get like a 2-to-1 rollup, which means that data stored in Druid is about half the size of the raw data volume. Some people get 1,000-to-1 rollups, where the data stored in Druid is 1,000 times less than the raw data, and really depends on the number of attributes and then the number of unique values within those attributes. If you have, as a number of dimensions starts increasing, as it does with flow data, it might be not that impactful, but it really varies from data set to data set, and it's just a trade-off that the operator has to make. How much do you want to spend on storage? How much do you want to spend for better performance versus what kind of fidelity of the data do we want to ensure?
So are you almost suggesting that there's 2 different operational databases, one that's designed for the last hour and another one that just does constant rollups?
What I would say is it's not like 2 types of database, but it's actually a more sophisticated data model. So within a system like Druid, it would be kind of one data set, but part of that data set is the raw data, part of that data set is a more rolled up data, and maybe part of that data set is an aggressively rolled up data where certain attributes are even stripped from the data to get better roll up. So I guess it would be in a single table. There's not a uniformity of how things are compressed and stored within a single table. You actually have homogeneity, but that's what's ultimately, I think, going to fit best with the use case while maintaining fidelity.
So, I mean, that's kind of my question is, I mean, I know you're contributing to Druid, so thank you very much.
Yeah.
Like we love using that. But you're comparing it to other things. Do you feel that some systems are better than others at doing?
Well, I think this like roll-up problem is not something that really any system has solved. I think the homogeneity in the roll-up is actually, like roll-up is a concept that's like native to Druid. It doesn't really even exist in a lot of other systems. Like if you were to use the elk stack, for example, you don't have this option even to compress your data. You're basically just storing the raw data as is. So you can always just do that in Druid, but I think Druid adds that additional level of sophistication to be able to start pre-aggregating some of your data if you need it for your use case. Thank you.
Hi, Dave Siegel, Siegel Group. Could you provide an example of what this approximated value looks like? You gave the example of the device ID. What does that look like? Like how is that approximation doing, and what kind of data is being lost in the process?
Yeah, so there's a range of approximation algorithms. They're also called like sketch algorithms, and some of them they're really around like set analysis. So you imagine you have like a set of elements, and one of the queries that you want to do is count the number of like unique items within a set. So if you have a dimension that's like device ID, and if you start having millions or billions of unique device IDs, most of the time you don't care about every single unique device. What you care about is the number of unique devices that you have at any given point in time. And this is something common with like user ID as well. So if you have a user ID or a session ID, you don't really care about every unique session. What you care about is the number of unique sessions that you have. So this is like the type of workflow that can be calculated approximately. This uses an approximation algorithm called hyperlog-log. And the idea is that as opposed to storing every single like unique user ID and then counting all of them, you store it in like a probabilistic mathematical data structure, which gives you about 98th percentile accuracy. But if you can start approximating some queries, you can get significantly better performance on those queries while significantly reducing storage as well. So if you have 1 billion unique users, maybe your approximate query gives you 999 million, but that's enough to understand kind of the trend, and that query can be done 10 to 100 times faster than if you stored every single user ID and counted all of them. Does that make sense?
Kind of. I guess I'd have to play with it, see what it's actually
Yeah,
it sounds like it would make the column mostly useless for a lot of different variables that have a lot of uniqueness.
It depends. So like the trade-off is that you lose information about, like using user ID as an example, you would lose information about every single unique user ID. But that's okay if all you're trying to do is count the number of unique users. If you actually care about the unique session IDs or user IDs and you have to maintain them, then approximation is not going to work. But if all you care about is counting the number of unique sessions and unique users, then approximation is something that can be potentially considered.
Okay. My other question related to scalability, like if you were to try and put this into a large network at scale,
yeah.
Does the hardware and those search times, do they scale in a linear way, or do they get more challenging? Do you get any optimizations as you get into the trillions of rows in the database and networks that are ingesting terabits per second values?
So with most distributed systems, when a system like Druid, which I talked about, they're designed to be horizontally scalable. So the idea is that performance, ingestion rates, and also query performance are going to be consistent even as your data scales. So as you go into petabytes of data, your query performance is actually, like if you're targeting for sub-second query performance at gigabytes and you go to petabytes, you should still be able to maintain that sub-second query performance by adding new hardware to the cluster.
So it doesn't break at some point when it just stops, you can't grow it anymore?
There hasn't been a cluster out there that's kind of pushed the limits. All systems I think have an upper limit, but I think of all real world data sets that we've ever seen, we've never seen that limit yet.
So what would you say the biggest system is that you've tested it with?
I've seen, so I used to work on a Druid cluster that was a few hundred petabytes of data, and then the data compressed down to about a few hundred terabytes across a few hundred nodes. I know of some systems out there that are about a few thousand nodes today, and these are some of the largest data sets in the world, some of the largest networking data sets in the world as well. So at that scale, still seems to be okay.
All right, thanks.
Thank you.
Paolo Lucente, NTT Communications. I don't have a question. Actually, I have a comment which is linked with the previous questions or comments. So although I'm not contributing to Druid myself, I'm a big supporter of Druid. In NTT Communications, we are using Druid for a variety of different use cases, ranging from flow collection to collecting BGP, SNMP, streaming telemetry, and things like that. And so, for example, there was this whole focus on the roll-up versus not roll-up and things like that, right? So, for example, I use flow collection mainly for business intelligence purposes, and in that case, it's a lot of data, and I use roll-ups because, for example, if you know, a specific flow was at whatever megabits per second at 5 minutes before or after, I don't really care because it's not forensics, it's you know, business intelligence. But for example, I have other data sets where I am collecting BGP or streaming telemetry, and there I really don't want to miss on any single point of data, and for example, the roll-ups are disabled, right? So I wanted just to clarify that, make that comment, and congratulate Fanjin for a great project.
Thanks, Paolo. Yeah, so much appreciated. So, you know, there's folk from Yahoo that presented, and Paolo spoke about some of his use cases. Druid is pretty widely adopted out there. There's a lot of public use cases online, public use cases about different companies at different scales. So encourage everyone, if they're interested, to check that out. If there's no other questions, want to thank everyone again for their time.